All right, we're going to take a look at another assumption we can use. Before we had a small k, now we're going to have a large k. And so this one's a bit more complex, but let's take a look at it. So it says find the concentration of copper 2 plus in a solution of 6.7 times 10 to the negative 4 molar copper nitrate. And we're told that it's a strong electrolyte, so it's going to completely dissociate. Upon the addition of 0.11 molar of ammonia. And we're given the Kf here is 1.7 times 10 to the 13, so a very big number. And then we're given the equation. So copper 2 plus is going to interact with 4 ammonias to form this copper tetraamine complex. And what we want to solve for is the concentration of copper at equilibrium. And so we want to start off with our Rice table naturally. We're given that the initial concentration of this copper is 6.7 times 10 to the negative 4. We're given that the initial concentration of the ammonia is 0.11. And then naturally, we're going to assume that none of our coordination complex has formed, and so it is equal to 0. And so now here's where things get a little bit more complicated. We see that our Kf is very large. Our Kf is very large. And so since the K is really, really large, that we know that the reaction will almost go to 100% towards products. Right? The K is very large, it's products over reactants, so we're almost going to transform all of our reactants into products. And so this is where we're going to start inserting this assumption. And so we're going to assume that this is approximately, that the change is approximately negative 6.7 times 10 to the negative 4 molar, right? It's the smaller of our two reactants, so it's the limiting reagent. This is approximately, negative 4 times this 6.7 times 10 to the negative 4 molar. And then our final concentration of the copper ammonia complex will be 6.7 times 10 to the negative 4 molar. And then we go into our next line. We know that this value isn't exactly going to be 0, right? We know this value isn't going to be exactly 0, right? We said it's only approximately equal to, and so we know that it's going to have some left over at the end. And so this is where it gets a little bit more tricky. This is what becomes our variable x, right? Because that's what we want to solve for in the end. For this one right here, we know that the equation is going to be 0.11 minus 4 times this 6.7 times 10 to the negative 4. And so what we can see is that this is a relatively big number minus a relatively small number. So we're just going to assume it's approximately equal to 0.11. If you want to go ahead, do the math and calculate the real value for this, you can go ahead and do it. There's no issue there. And then this value right here will be 6.7 times 10 to the negative 4 because 0 plus this number is equal to this number. And so now we can write our equation for our Kf. Our Kf is going to be equal to the concentration of our products, which in this case is this copper tetraamine, over top of our copper, times the concentration of this ammonia to the 4th. And then what we have to do next is just simply plug in our numbers. So the concentration of copper is going to be X. The concentration of our ammonia is going to be 0.11. And then the concentration of our complex is going to be the 6.7 times 10 to the negative 4. And then, of course, we know all of this is equal to our original Kf, which was 1.7 times 10 to the 13, right? And so now we can plug these values in here. So in this case, we have 6.7 times 10 to the negative 4 over top of x times 0.11 to the fourth is equal to 1.7 times 10 to the 13. And then what we have to do is solve for x. So go ahead and do the math there. Shouldn't be too difficult. We get a final value of x to be 2.7 times 10 to the negative 13. And remember, x was our value of our copper 2 plus concentration. So this is equal to the concentration of copper 2 plus at equilibrium. And then that is our final answer. Now, we did quite a few assumptions, right? So is there any way we could check whether our assumptions are valid? We can't use the 5% rule in here, but what we can do is plug our numbers back in and see if we get K. So remember, Kf here is the concentration of the copper complex over the concentration of our copper. Right, and then we said the concentration of the copper complex was 6.7 times 10 to the negative 4. The concentration of our copper was 2.7 times 10 to the negative 13. And then our concentration of ammonia was 0.11 to the fourth. Plug and chug those in, and you'll get 1.7 times 10 to the 13. Right, and that is our exact value for K that we were originally given. And so we kind of double checked our answer. And since we got the same value of our K, that means that our assumptions didn't mess up the math too much and that it's valid, right? So the final K matches the given K. So the assumptions are okay. So this was one way to do these types of problems. When you have these large Ks, there are other ways to do these problems. If you want to use some different way, that's totally fine with me. You just have to make sure that it gets you to the correct answer at the end.